Okay, let's move on with our silicates. Before the exam, we discussed examples of one-dimensional silicates. Now let us move over to two-dimensional silicates, which are also called phyllosilicates. So let us first think about what would be the most simple phyllosilicate that we could make. So the most simple phyllosilicate would be made of one chains with a periodicity of 1, and these 1 chains would just be fused together in a periodic array. And you can see how this is being arranged over here. Okay, so here you have one of such a one chain. That means the periodicity in this chain is 1. Okay, so that means that each of these tetrahedra, when translated into the direction of the chain, will superimpose the next tetrahedron in the chain. Okay, and then we just fuse these chains together. Okay, so you can see here, to form sheets, whereby within that sheet we would have now exclusively corner sharing tetrahedra, and all oxygens would be connected to 2 silicons, okay, in both directions. Okay, in this direction you see that, well, the corners are being shared, and that means that each oxygen is actually bound to 2 silicon, which are in the centers of 2 adjacent SiO4 tetrahedra. We also see that in this direction here, each oxygen is actually being shared by 2 tetrahedra. Okay, so this means that each oxygen is being bound to 2 silicons in the center of 2 adjacent tetrahedra. So now we can think about what would be the composition of this silicate. Can anybody answer this question? The answer is that when all the oxygens are actually bound to 2 silicons, none of the oxygens carry a charge. And so that sheet would actually be charge neutral, and for that reason, the composition of that sheet must be just SiO2. And that means that this would be a polymorph of SiO2. Okay, one possible polymorph of SiO2. Okay, but silicon dioxide does not realize this structure in practice, even though it's possible to write the structure as on the sheet of paper for energetic reasons. So in practice, silicon dioxide only makes 3-dimensional structures, for the simple fact that all these 3-dimensional structures are energetically more favorable than such a 2-dimensional structure. However, as a synthetic chemist, one may indeed think about, well, how could you actually also realize such a SiO2 sheet structure? Because it could still be kinetically stable. So that means that if I actually found a pathway that would form this that kind of structure, then this structure could still be kinetically stable, because the activation barrier, okay, for this structure to form into a thermodynamically more stable 3-dimensional structure may actually be significantly high. Okay, but thus far nobody has actually found a pathway how to make a layered form of silicon dioxide. Okay, so now does this kind of structure never appear in nature? This is actually not true. So in mercury iodide, this sheet structure is being realized. Okay, now you can easily explain this by the fact that mercury and iodide are elements that have very different properties than silicon and oxygen. Okay, therefore, it is not surprising to us that they form they prefer fundamentally different structures than silicon dioxide does. Okay, so this most simple silicate is not realized in nature. However, we have many phyllosilicates made from two chains where the periodicity is not one but two. Okay, so in these kind of silicates, we have always Si2 or 5 2 minus polyanions. And that means that you can identify such a phyllosilicate often just by looking at its empirical formula. So if that Si2 or 5 unit appears in the empirical formula, you may actually suspect that this may be a phyllosilicate. Okay, and because phyllosilicates with two chain structures are very common, you may actually suspect that this is a two-chain, two-chain phyllosilicate. All right, so now there are many variations of the theme possible, how we can realize phyllosilicates from two chains. And 4 of them are illustrated on the slide here. So here you see the first one. This is in a way the most simple one. So you see first of all that you have these chains now having a periodicity of 2. That means that when we go into this direction, we have to go along 2 tetrahedra until we arrive at a tetrahedron which superimposes the original tetrahedron. Hence the periodicity is 2. Okay, and now you see that many of these chains are actually fused together to form a layer. Okay, so here would be the second chain. Yeah, so here that would be the third chain. This would be the fourth chain here, and so forth. So now when you analyze the sheet structure that results, then you find that all the tetrahedra, they point into the same direction. Okay, you see this actually more clearly here. Okay, when you look actually parallel to such a sheet. Okay, all these tetrahedra here, the tips of these tetrahedras, they all point up. Okay, so now look at the charges that there are at these tetrahedra, and you see that, well, all the tips of these tetrahedra, they must contain terminal oxygens, because obviously these oxygens are not connected to another silicon. And for that reason, all these oxygens must carry a 1 minus negative charge. Okay. Therefore, these layers are strongly polarized. Okay. So you have actually layers of negative charges on that surface, while you have no negative charges on the other opposite surface of the layer. Okay, you can easily see here that these layers, these negative charges will strongly repel each other. And therefore, such sheets are only realized when these layers are condensed with other layers that reduce the number of negative charges. Okay, so how that is being realized, we will see later. Okay, but individual sheets like this, okay, which are not further condensed with other sheets, are not known, okay, for electrostatic arguments. Okay, so now here you see a second example in which the polarization within a layer is being reduced. So you see again here you have chains with periodicity of 2, but now one chain has the and these are the white ones, has the terminal oxygens which carry the negative charge point down, okay, shown here, while these red ones, okay, which then the next chain here have the terminal oxygens point up, okay, and this principle alternates throughout such a layer, okay. So now you do not have these strongly polarized layers anymore. Rather than that, 50% of the negative charges are lying below, well, that line here, while 50% of the charges here are lying above this line here, or that surface. Okay, so for that reason, these kind of layers are much more common. An example is lithium 2 Si2O5. Okay, there are also other possibilities how we can take away the polarization. You see here another possibility. So you see here in one 2 chain, the first tetrahedron points upwards while the next tetrahedron points downward, and that principle alternates throughout that chain. Okay, and then multiple of these chains are interconnected to form these sheets here. Okay, so here the second chain, again made of alternating of tetrahedra alternatingly pointing up and down. So here you have the third one, and here you have the fourth one, and so forth. Okay, so now again you have 50% of the tetrahedra pointing up and 50% of the tetrahedra pointing down. Therefore, again, you don't have polarization across the layer. So this is also energetically pretty favorable, and there are numerous examples. The one example is a mineral which is called the Phyllosilicates, which has the formula magnesium 2 Si4O10. All right, so here's one last example. So in this example, we again have chains in which all SiO4 tetrahedra either point up or down. Okay, so in these white chains, again the tetrahedra point down. In these red chains here, the tetrahedra point up. But again, the chains are interconnected in a different way. So now, in this example, we have basically 2 chains of the same type interconnected, okay, followed by 2 chains here and here of the other type being interconnected. Okay, so now basically in this case we have 4 consecutive tetrahedra that point up and down respectively, while here we had 2 tetrahedra, consecutive tetrahedra or adjacent tetrahedra that point up and down respectively. Okay, but I see also in this case here, Overall, the layer is not polarized because the number of tetrahedra that point up equals the number of the tetrahedra that point down. So this structure here is realized in the example barium 2 Si4O10, okay, or barium Si2O5. We wanted to reduce this to the empirical formula. All right. Now we can also make even more complex phyllosilicates. However, as I mentioned before, the more complex we make the structures, the more rarely we encounter them, but there are beautiful examples with more complex structures that are worthwhile to look at. So here you have just two examples. So in both these examples, the layers are not planar. Okay. So here in this first example, you have 4 rings. Okay. So rings of 4 tetrahedra, which are arranged in sheets. Okay. So here you have the first 4 ring, you have the second one, you have the third one, and you have the fourth one, the fifth one, the sixth one, the seventh one, the eighth one, and the ninth one. Of course, there are more, as this is an infinite structure in 2 dimensions. Now, in all these 4 rings, the tetrahedra point up. Okay, so here you see the terminal tetrahedra, terminal oxygens all pointing up. So these kinds of 4 rings are not interconnected. Okay, so this one is not directly connected to this one, for example, and this one is not directly interconnected to this one. Okay, so now, however, we have more 4 rings, but in these 4 rings, now the tetrahedra point down. Okay, and these are these 4 rings here. Okay, and well, now the tips of these tetrahedra are interconnected with the tips of the other type of 4 rings. Okay, so for example, this tetrahedron here and that tetrahedron here share an oxygen, and that tetrahedron here and that tetrahedron here corner share an oxygen, and so forth. Okay, so now you see that this overall gives a 2-dimensional layered structure, but the layers are not completely planar anymore. Okay, so these tetrahedra would be completely in a plane, and these 2 tetrahedra would be completely in a plane, but the overall structure would be more wavy, right? And now the interconnection of these 2 types of 4-membered rings create 8 rings. Okay, so you see such an 8 ring here, and this 8 ring is now not planar, so it would consist of 1, 2, 3, 4, 6, 7, 8 of these tetrahedra. Okay, 4 of them would point up. These are these 2 here, and 4 of them would point down. These are these 2 here. Okay, so an example in which that structural motive is realized is the gillespite. So this is a barium iron silicate. Okay, so here's another example where we have even larger rings. So here we have actually 4, 6, and 12-membered rings. You see here that within a 6-membered ring, all tetrahedra point into the same direction. Okay, so these tetrahedra here point down, but these six-membered rings then have adjacent six-membered rings in which all the tetrahedra point up. Okay, so one six-membered ring is shown here, then another one is shown here, and another one is shown here. Okay, and each six-membered ring in which the tetrahedra point up is surrounded by three six-membered rings in which the tetrahedra point down. Okay. So this structural motif creates additional rings. Okay, that creates these four-membered rings here, in which two tetrahedra point up and four tetrahedra point down, and it creates these very large 12-membered rings. Okay, with alternating pairs of tetrahedra, in which pairs either point up and or point down. So an example for this kind of structure is a pyrosmalite. That is manganese 16 Si 12 or 30 OH 18 Cl2. Okay, so there was a chloride ion somewhere in that fairly open structure. All right. So now let's go to phyllosilicates with double layers. In the previous examples, they were all just single layers, but we can actually fuse two layers together to make double layers. Okay, so we previously already discussed that when we have a single layer like this single layer is not stable in itself because it's so strongly polarized, so all of these tetrahedra point up. However, we have now the possibility to fuse two of these layers together to make these terminal oxygens here actually bridging oxygens. So that removes the charge. All right. Now, this would actually realize this kind of structure here, in which basically one single layer in which the tetrahedra point up would be fused with another single layer in which the tetrahedra would point down. So now that leads to the fact that you actually remove all the negative charges from the structure, because now all the terminal oxygens become bridging oxygens. And that means that this structure here would represent another possible polymorph of SiO2. Okay. However, again, nature doesn't realize this possible modification or polymorph of SiO2 because nature prefers three-dimensional SiO2 structures over two-dimensional SiO2 structures. However, this kind of structure has its place in reality in some ways because we can actually remove some of the silicons from these structures by aluminums. Okay, so we have then Al4 tetrahedra. Okay, and when you surround aluminum tetrahedrally, then that aluminum carries a formal negative charge. Okay, and that means that the entire layer then carries a formal negative charge depending on how many aluminums are in there. And then that negative charge will need to be counterbalanced by cations that are in between the layers. Okay? And that's realized in the compound calcium Al2 Si2O8. Okay, you can see that now 50% of the silicons have been replaced by aluminums. Okay, when respective negative charges, which are overall 2, because we have two aluminums here in that partial structure, are compensated by a calcium 2 plus ion. And these calcium 2 plus ions, as you can see here, are placed in between the layers. Okay, so now we can also have phyllosilicates that are in which an tetrahedral layer is condensed with an octahedral layer, whereby in the octahedral layers we would have either magnesium 2 plus, or we would have aluminum 2 plus. Okay, so these octahedra would therefore be either aluminum O6 or magnesium O6 octahedra. Okay, so if the element is aluminum, then these octahedral layers are so-called dioctahedral layers. And when the cation is magnesium 2 plus, okay, then we have trioctahedral layers. Okay, so you see that the trioctahedral layer realized here, and you see that this trioctahedral layer has is a dense layer of corner sharing octahedra, okay, which you see here in green. Okay, and now some of the corners of these octahedra share their oxygen atoms with the terminal oxygens of a tetrahedral layer, okay, whereby this tetrahedral layer again has silicon in the center. All right, so I also wanted to mention that the arrangement of the atoms in the trioctahedral layer is similar to cadmium iodide, which we discussed previously in the course. Remember, cadmium iodide, we have a hexagonal close packed structure in which 50% of the octahedral holes are being filled, whereby that filling occurs in a layered fashion. Okay, so in one layer we have all the octahedral holes completely filled, while in the next layer we have the octahedral holes completely empty, resulting in a sheet structure. So now in a dioctahedral layer, we have aluminums in the center of the octahedron. So the aluminums are aluminum 3 plus ions. So the aluminums carry one more positive charge than the magnesium 2 plus ions. So for that reason, we need less many aluminum ions to compensate the charges of the oxide 2 minus ions in the structure. So for that reason, we only need to fill 2/3 of the octahedral holes in the octahedral layer. Okay, 2/3. For that reason, this is called the dioctahedral layer, derived from 2/3. Okay, so that creates holes in that octahedral layer, as you can see here, compared to here, whereby still the octahedral layer is condensed with the tetrahedral layer. Okay, so that means that some of the oxygens within the octahedral layer are being shared with terminal oxygens within the tetrahedral layer, which is made of SiO4 tetrahedra. Okay, so now again, because the terminal oxygens of the tetrahedral layer, which formerly carry the negative charge, do not have a formal negative charge anymore because they are shared with the octahedral layer. So again, that takes away the polarization of the tetrahedral layer, and that leads to a stabilization of that tetrahedral layer. Okay, so now let's have a closer look at the electron neutrality in these structures. By the way, these phyllosilicates are called one-to-one phyllosilicates because we have one tetrahedral layer connected to one octahedral layer. You see here basically a magnification of such a sheet. So you see here the tetrahedra, and you can see here some of the octahedra. So you can see that we have different coordination numbers for the different species. So all silicons are tetrahedrally coordinated, and of course all aluminums are octahedrally coordinated. But what about the oxygens? So we can actually separate the oxygens in oxygens being part of 3 different layers. So all these oxygens here would be in layer A. Okay, they would belong all to, they would be only bound to silicon. Then we would have here oxygens in layer B, which are being bound both to silicon and aluminum. And we would have here oxygens in a layer C, and these oxygens would only be bound to aluminum. Okay, so let us look at the coordination number of these oxygens more closely. You can see that in layer A, all the oxygens are being bound to 2 silicons. Okay, but now you see that in layer B, we have 2 types of oxygens. So we have these ones here, and these ones are bound to 2 aluminums. Okay, so are bridging 2 aluminums. But now we have in addition these ones here, which are bound to 2 aluminums. Yeah, but in addition to that, also to a silicon. So they actually have the coordination number 3. Okay, so this means that they have formally a positive charge. All right, so now we can actually see, so again in layer C, I forgot to say this, we again have only oxygens which are bound to 2 aluminums. Okay, so now we can actually derive the charge of such a layer from the coordination numbers. Okay, so we have aluminums in the coordination number 6, and all these aluminums have formally a 3- charge. Okay, we have oxygens which are having the coordination number 2. So these oxygens do not have a formal charge. Okay, then we have here the silicons in the coordination number 4. So silicon in the coordination number 4 doesn't carry a formal charge. And now we have here these oxygens with the coordination number 3. Okay, and these ones carry a formal positive charge. So within the layer, these different species have the stoichiometric ratio 2 to 7 to 2 to 2. Okay, so now we have 2 times 3 negative charges in the aluminum. Okay, so that gives 6 negative charges. And we have 2 times 1 positive charge here at the oxygen. Okay, and -6 plus 2, well, that gives -4. And that explains why these layers overall have a 4- negative charge. Okay, So this charge within these layers has to be compensated somehow by a cation. Okay. So now in the most simple case, these cations are protons, and these protons will now coordinate to the most basic sites within that layer. Okay, so the fact is that for reasons of electronegativity, basically, that the O2 minus ions in layer C have the greatest basicity. Therefore, these protons, 4 of them actually, coordinate to oxygens in layer C, which are oxygens basically that coordinate to aluminum only. Okay, so therefore you actually have hydroxyl groups on that side of the layer, which is the octahedral layer. Okay, now what are examples of that? So the example in which this structural motif is being realized is the so-called kaolinite. So that's a very important mineral and also a very important starting compound for ceramic products. Okay, and you see here the overall structure. So if here an AOL6 octahedral layer fused with an AOL4 tetrahedral layer, okay, whereby you have 4 protons, as shown here in the formula, that basically protonates oxygens on that side of the octahedral layer. Okay. So if you can do all of the same with magnesium. Okay. So when you use magnesium, you fuse the tetrahedral layer with a trioctahedral layer, as shown here. Again, such a layer has a negative charge overall, and you actually need 4 protons to counterbalance the negative charge. And again, these 4 protons will coordinate to the oxygens of layer C, because again, this layer C is contains the most basic oxygens. Okay, and then the mineral that results from that is called serpentine. Okay, so that's the most important trioctahedral one-to-one phyllosilicate. All right, so now the fact that the protons coordinate to layer C leads to certain properties of this type of phyllosilicate. So they are relatively hard, and that is because you have hydrogen bonding in between the layers. Okay, so now you can easily imagine that when you have here hydroxyl groups on that side of the octahedral layer, these hydrogens can make hydrogen bonds to the oxygen of an adjacent tetrahedral layer. Okay, so despite you having a 2-dimensional structure, you have a relatively hard material. So these hydroxyl groups on the surface of the octahedral layer also lead to a fairly high hydrophilicity of their respective material. So these materials swell fairly easily in water, and the layers can even exfoliate, in particular when you actually use a basic solution, because then these protons get neutralized by hydroxides. Okay, and you can actually intercalate metal ions, for example, sodium, in between these layers, and then these layers exfoliate. So they are kind of going in solution. Okay, but there are now large structures being in solution. So therefore, these solutions tend to be quite viscous, and they show even thixotropy. So they behave kind of like ketchup. Right? So they flow very slowly until, like ketchup, when you actually exert mechanical force, they all of a sudden flow very quickly. They also have ion exchange properties, so you can actually exchange the protons by other ions. For instance, when you treat such a material with a basic solution of sodium carbonate, you can actually intercalate, can exchange the protons by sodium, for example. They're also thermally relatively unstable, okay, because you have actually interactions of the hydroxyl groups here at the aluminum with the tetrahedral layer, and when you just heat that enough, an octahedral layer can start to chemically react with an adjacent tetrahedral layer under the elimination of water, and then this converts into a three-dimensional structure. Okay, so now we discussed one-to-one phyllosilicates. In addition to that, we can also have what is called a two-to-one phyllosilicate. So in this case, we have two tetrahedral layers sandwiching one octahedral layer, okay? Whereby, again, this octahedral layer can either be a dioctahedral or trioctahedral layer. When we have a dioctahedral layer, then the octahedral layer contains aluminum. When we have a trioctahedral layer, our octahedral layer contains magnesium. So one important material and also mineral associated with this kind of structure is the pyrophilites. And the pyrophilite, we have aluminum that are arranged in a dioctahedral layer. So again, these layers have a charge. So overall, we have here a 2 minus charge in these layers, and this charge can be compensated by protons. Okay, you see, in this case, we will have 2 protons per formula unit. So now again, the protons, they coordinate to the most basic sites, and the most basic sites are actually, again, aluminums, oxygens, which are coordinated to 2 aluminums. Okay, and coordination of these protons to these oxygens creates hydroxyl groups. But now you see that these hydroxyl groups are within the layer. Okay, they're not on the surfaces of these layers, because the surfaces of these layers are now tetrahedral layers only. Okay, so now if you replace aluminum by magnesium, then you realize a material which is called talcum. So you probably all know talcum powder, which is, for instance, used as a baby powder. Now in this case, you have magnesiums. Okay, again, you have 2 protons, but again, these protons are basically within the layer because they coordinate to the oxygens that are bound to aluminums, and therefore on the surface of the overall layers, you do not have any hydroxyl groups, right? So now that gives these 2-to-1 silicates very different properties to the 1-to-1 silicates. So we have no OH groups on the layer surfaces. And this means that we have no very polar groups on the layer surfaces. And that leads to a significant hydrophobicity, significantly higher hydrophobicities of these materials in comparison to the 1-to-1 phyllosilicates. So you may have actually felt talcum powder, okay, and the talcum powder feels like feels a little bit fatty, right, like fat, and that's because of the hydrophobicity of the layers. Okay, so we have also no hydrogen bonding in between these layers. Okay, so now there are very weak interactions only between these layers, and therefore the whole material becomes extremely soft. Okay, so talcum powder feels extremely soft just because of these very weak interactions in between these layers. So we also now have a much higher thermal stability, especially for peripherolite. That is again because now we have no reactive groups on the layer surfaces. Therefore, it is very hard to make these layer surfaces chemically react with each other, which leads to very high thermal stability. These layers also are very little compressible, especially in peripherolite, and they're also very good thermal and electrical insulators, and in fact they are often used as such when these materials are being used as functional materials. All right, so another important class of 2-to-1 phyllosilicates are the micas. So in these micas, some of the silicon 4 plus ions in the tetrahedral layer are replaced by aluminum 3 plus. Okay, so now we have additional negative charges because tetrahedrally coordinated silicon has no charge, while tetracoordinated aluminum has a form of 1- charge. So therefore, the layers overall get a negative, a more negative charge, and that charge is now can now be compensated by cations, which are in between these layers. Okay, and these cations can be, for instance, potassium, so sodium, potassium, cesium, and other ions. So, for instance, mica structure, an example for mica structure is, for instance, biotite, which is a potassium, iron, magnesium, alumosilicate. Also, another example is muscovite. So in this case, we have dioctahedral layers because we have aluminum instead of magnesium here. Okay, so the exact composition is potassium, aluminum, silicon, aluminum, oxygen, hydroxide. Okay, you see here the structures. So you see here the 2-to-1 layer. Okay, and you see now here you have ions. Okay, for instance, potassium or iron or other cations in between these layers. So these are very common materials. Minerals in the Earth crust, about 3.5 weight% are of the Earth crust are made of that kind of material. All right. Now I see we are out of time. There's a little bit more to say about this, but I can postpone this to the next class, so we can actually stop here.